Since the first satellite was launched in 1957, the number of active satellites has grown exponentially. Today, there are over 8,000 operating satellites circling our globe. The overwhelming majority of these satellites are in low Earth orbit, or LEO, including the International Space Station, the Hubble Telescope, and the Starlink constellation. As the number of LEO satellites increases, so does the complexity of their electronics. Advances in fundamental components for LEO satellites will be the focus of today's discussion, so stick around to learn more. Welcome to Tech Chat, sponsored by Mouser Electronics, where we chat with engineering experts about the latest technical innovations that are shaping and reshaping our world, or in today's case, space. Today we welcome back friend of the show, Ron Demcko. Ron is a senior fellow at Kyocera AVX. It's good to talk with you again, Ron.
Thanks, Dale. It's great to be here.
And before we really dive into the details of what you have for us today, since we're going to be talking about LEO satellite components, can you give us some background on why this is such an exciting topic these days?
Absolutely. Well, LEO sats are experiencing quite a high rate of growth. Basically, the sector is growing at about 20%. And the vast majority of individual spacecraft are these small platforms that we're here to talk about today. Now, they're becoming more practical as time passes by. Part of that is because of the launch platforms or the launch delivery systems getting more cost effective. It used to cost $25 per gram of hardware to be delivered. Well, that number is quite a bit lower now, and it holds promise to be lower. There's new LEO hardware. So there's totally new configurations of LEO sats, and then there's also very good developments within the subsystems. So the LEO sats themselves are getting much more complicated and capable in terms of either processing things for like Earth observation or communications links, maybe their navigation, maybe their industrial like mining, farming, or maybe their R&D. But they're very useful in all of those types of applications. So it's a great sector to be in.
Well, that's really exciting. Well, can you start out by giving us an overview of today's presentation?
Yes, no problem. Well, what we'd like to do is break it up into three parts. First off, talk a little bit about the satellite needs. Where does Kyocera AVX fit in? And then what type of problems do we solve? With LEO sats, there's a very interesting situation that we have. These platforms can have a very low signal propagation delay. So that means less latency. And of course, less latency is very interesting to the end users. The reason I mention this at this point in time is that a good deal of effort is placed on optimizing that RF and the digital processing hardware. In optimizing them, the power budget becomes quite important. And there's solutions and efficiencies that can be gained by choosing the right passives. So, it's a hardware situation that is changing, but there's great solutions if you're aware of what's out there. And speaking of what's out there, let me give a plug to NASA. They have a great publication, State of the Art Small Spacecraft Technology. It's a report. It comes out from Ames Research Center at Moffett. So the Moffett Field people have done a tremendous job. That report is dealing with basically the state of hardware. It does not cover any of the export limitations or proprietary or military advances in the sector, but it nonetheless is very comprehensive and a great place to start for further details.
Well, that sounds great. We'll have to check out that resource. One of the things I wonder as we talk about the LEO orbit, is it more similar to just more traditional aerospace kind of requirements or GEO? I mean, there's kind of a big gap there in more ways than one. Where does LEO kind of fit in that spectrum?
That's the million-dollar question. It's a tremendous question that you ask. And I'm afraid that the answer is going to vary by individual spacecraft and platform and its intended use. So there are some instances where the LEO sats are actually using automotive grade parts. Then there's others, and perhaps it's hard to say a majority, because it does. The majority that I deal with are working on COTS plus and space grade parts. Certainly, we're happy to help with any type of satellite or satellite constellation. But that question that you ask is very applicable. And, part of the reason for that is that the ICs themselves and the semiconductors have advanced so quickly that in some cases, the actual parameters of the capacitors that are needed are not yet in the military performance spec arena. There are slash sheets that are out there, but the rate of change is doing nothing but accelerate. Also, having said that, I'd like to say that the military and DLA, they've done a great job in getting these standards out quicker. So the whole situation from hardware to delivery systems and design, it's really accelerating. That's part of the excitement, I think, of the whole sector.
Yeah, it really is an exciting time to be involved and see what's going on in this industry.
Okay, so on slide 3, we're showing a very generic block diagram of a LEOsat. The 6 blocks above the circled subsystems, they actually could be anything. Now, they might be some IR cameras, they might be a standard camera, might be radar, who knows, right? But I think the whole point is to say that around any standard LEOsat, you're going to have all of these different options that are configured by the end user. As you mentioned, and we commented in the previous slide, there are standard devices and COTS, and then there's mil-aero type of devices that are used in each subsystem, depending upon the type or mission of each satellite. But regardless of that, we generally speak of the power supply of up in the upper left corner. Then we have some control unit on the bottom left. We've got some sensors, analog front end, things along that line, upper right, and then actuators, drivers, some more power related circuitry in the bottom right. Generally, we could break things up and say that there are RF devices that can be optimized to perhaps make the uplink and downlink, the noise levels, more attractive for the end users. There is some concerns in the power supply. How can we have more stable voltage, either stable voltage with radiation or with aging of the spacecraft? It's important because that might set the noise levels for some of the hardware. So we talk a lot about tantalum devices, ceramic devices, and then, of course, we have to worry about communications interference between these subsystems. We'll touch on the filter devices. And then, of course, we have to worry about timing throughout the whole system. And there's some great solutions that we have there.
Yeah, it's fascinating for me to think about the fact that, when you talk about radiation hard electronics, we're often thinking about bit error rates and memory getting corrupted. But it's going to affect, as you mentioned, aging of the power supply and the analog stuff.
That's right. That's very important to mention, too, because as this hardware gets more powerful, it will in turn consume more power to achieve its functionality, right? Mm-hmm. So given that we have semi-fixed budgets on the solar panel size and incoming power and some limitations with batteries and such, we have to very efficiently convert that power. So that's a very big theme. Efficient, reliable power conversion. And it's really one to concentrate on first. Luckily, there's some great actives that are out there. We're working directly with those companies, but that's really a very fundamental place to start to worry. Yes.
That makes sense.
Okay, so in terms of ceramic capacitors, well, a lot's been occurring in the world of ceramic capacitors. First off, there's new materials, there's new designs and processing. There's a much larger database, and the result of all of those developments have actually been whole new families of multilayer ceramics. Now, they may be based on base metal electrodes rather than precious metal electrodes. That allows us to get a military grade part that has high capacitance per unit volume. That's very attractive. There's also low inductance parts that have come into play. So a lot's been changing from a materials and processing point of view. In this slide, we're looking at essentially COTS parts on the left. And then the 3 columns on the right are talking about military performance specs, either MIL-PERF 123, 3535, or 55681. The one thing that you'll notice is, what's the difference between COTS and a military grade part? Well, generally speaking, you could say that COTS may tend to have some of the extended values, whether that be voltage or capacitance per unit volume. Now, that doesn't at all mean that they should be the dominant part in the circuit. There's very good history that shows the military perf parts have the reliability, the pedigree to work on those critical functions within the mission. And there's also areas that the mil parts excel in. For instance, the mil perf 32535, the center red column, there's actually low inductance ceramic capacitors that have the ability to reduce the part count around a decoupling field. So that's important in the sense that we could reduce the weight, the number of components, the number of interfaces, and therefore potentially the number of soldering errors that could occur, etc. So choosing the right ceramic capacitor can very greatly impact that design. Now, generally speaking, everything we have on this slide is small signal, low power.
And then going back to the previous slide and kind of your discussion there, as you're designing these different blocks, you want to make sure you're thinking about all the options here, because some parts of that satellite system might need the mil-spec part, but maybe the COTS Plus is better for a different piece of that same satellite.
Yes, that's exactly true. And in fact, there have been some very good position papers that define what is allowable. Maybe allowable isn't the right word, but what's possible to be used and get away with. And that's probably not a good description either. But Aerospace Corp has a very good paper out on that. And it basically talks about if it's a non-critical type of function, we certainly could potentially use a non-military or COTS type part. So yeah, really encourage people to look into that. What we have here is another look at ceramic capacitors. It kind of goes and expands upon our discussions about power conversion and about weight and about size. I guess weight and size are implied in the LEOsat. They're typically relatively small satellites from a weight and physical size point of view. So what we have is a limitation on the possible volume of the power supply, for instance. So the part on the right-hand side is a stacked ceramic capacitor. There's military specifications for that. There's actually DLA drawings, etc. But this type of part is actually a very low inductance, low ESR, high capacitance part. It's a bulk capacitor. And those combinations of parameters are important because it allows for very efficient power conversion, and in turn, that efficient power conversion could be a small physical size. So stacked ceramic capacitors hold an awful lot of promise in that circuit. Now, later in the slides, we'll show that other components could be stacked, in particular tantalums or tantalum polymers. We'll go over to the leaded caps before I get to that. And leaded caps are sometimes forgotten. Those tend to be module and sub-unit assembly mount type applications, but there are radial, there's the molded 2-pin dip, there's some axial parts, and there's actually some axial parts that have certain limitations upon where they could be sold. So the North American design teams that are listening to this may want to consider what else is available in the axials in some instances.
Well, that's a fascinating discussion, maybe for another day, of why, it looks like one capacitor looks like another one almost, but important to stay abreast of those restrictions.
Yes. And in fact, some of these components can actually enable whole subsystems on the spacecraft. So what we're seeing here are some of the more public scenarios, but of course, there's many other enabling types of technologies available with further discussions. So we get to the world of tantalum, and tantalums have had an incredibly good and solid past history with great success in flight. They offer a very high capacitance per unit volume. They have a very good operating voltage associated with them, and their stability is really quite admirable. There's zero DC bias, there's zero AC bias, And as we get into the world of high-speed digital processing on platform, those lesser parameters, the ones that kind of didn't matter 10 or 20 years ago, now they're quite important, and there's something to look out for. So what we're seeing here are two different groupings of components. The ones on the right, that's actually a small selection of the military performance specs, the 55365. Now, there's many different slash sheets associated with that document. Let's look at the center column, the CWR15. That's a TBC type part. It's available in COTS Plus as well. But the importance of that part is, if we look at a 1206, that part, let me describe it a bit further. Tantalums typically have a lead frame that they are welded and attached to. And then that lead frame is encapsulated in a plastic. So not all of that unit volume of the component is actually a working device or one that contributes to the capacitance of the component. It contributes to the reliability, but not necessarily to the capacitance. Well, there's a new technology out. I guess I say new, it's been out there for a few decades, but a new way of thinking that allows you to have a high reliability capacitor, a tantalum, that does not have that case. And by eliminating the case, you reduce the inductance of the part. That's always very attractive. Reduced inductance gives you a higher frequency response. And further, it allows you to have a much higher capacitance per unit volume. So if we compared a 1206 of that CWR15 to a 1206 of a CWR11, you could see that we're something on the order of 15 or so times capacitance in the same unit volume. That's super important, right? I bring this up because tantalums have the ability for a very high density capacitance per unit volume. Now, the other thing is just taking that CWR15, that 1206, right? It may have a weight depending upon the values within the part. The weight could be 0.016 grams at the lightest or 0.42 grams at the heaviest. So it's a tremendous technology. Please look into what the various slash sheets of these mil specs could offer. On the far left side, well, there we're showing COTS. And that commercial off-the-shelf example is kind of abbreviated. There's basically 11 different types of COTS series that we happen to offer. Briefly going through it, the TBM is a very low ESR part. It's a Weibel grade capability. It has 3 components in it, and it has different surge options. The TCP is actually it's a stacked module. So it kind of corresponds to the intent of the prior stacked ceramic capacitors. It might be a power supply unit. It might be a hold-up unit. TCHs are a fully hermetic component with extreme environmental range capability. That's a good overview of the first part of tantalums and tantalum options.
You know, it's really interesting to hear you explain all the fascinating technology behind these, the advances have been made, because they don't get nearly as much attention as transistors do in the advancing node, the semiconductor. But really what has happened in the last few decades, and I think it's accelerated even recently in these kind of components, is pretty fascinating and important as well.
Yes, it's very true. We can give you an example of where things have changed. When I was in college, they said that a farad capacitor would be the volume of the whole lecture room. And it was quite a big lecture room. It held maybe 200 people, right? Mm-hmm. Well, now we are building supercapacitors that have approximately 1.5 farads or so in a cubic centimeter. Put another way, in a Coke can type volume or soda can type, we can put about 3,000 farads in there. Low voltage, but still very significant. And you're exactly right. Technology has shifted and changed just as much for us as the semiconductor guys.
Yeah, many orders of magnitude in the changes. So that's a great example of showing how that has advanced.
Yes, and now to go a little bit further and talk about actually one of those advances, tantalum polymers. Well, this is a new material system in the world of COTS, or relatively new. And in fact, there's a military performance spec on tantalum polymers. Here, we're just showing some of the COTS But please do be aware there's a tantalum military performance spec that is now in play in the industry. And generally, the polymers, we could say, are attractive because they have approximately 1/8 of the ESR than tantalum part. So put another way, that 1/8 of the ESR allows us to have about 8 times the RMS current. And in the world of power conversion, higher RMS current per the same unit area or volume is very attractive. And tantalum itself is only a 20% derating. Now it's really interesting. I guarantee that you're driving on these in your daily vehicle, whether it be an electric vehicle or an internal combustion engine. There is a series of tantalum polymers. It's the TCQ series. It's not shown here, but it's auto grade. And they go up to about 470 microfarads and at 50 volts and standard military operating range. And the leakage is only 0.1 CV. So that's attractive. Now, if we kind of extend that out and start looking at what's on the chart here, we can see the TCSs. That's essentially an upscreen multi-anode part. The TCBs, or maybe we could say the standard polymer COTS type part that's out there. The TCD is a DLA drawing part. And then we get to the ones on the right, the TCH and TCH stack. That's really interesting. That's where we've taken essentially this polymer, we put it in a hermetic package, and we've stacked it for efficiency from an XY point of view. One of the things to note, though, is that it's up to 100 volts. So that's quite attractive as we get to high level or higher voltage power conversion on spacecraft. It's a very efficient and an exceptionally high reliability part to fly with. In the world of radiation, we wanted to take and provide some data. And there's certainly a lot more data, much more data than this available. What we're showing is 2 different series. It's a TRJ and a TCQ type part. And what we're looking at, we wanted to show the performance of 2 different types of series in radiation fields. And what we're looking at is the exposure to and the variation of capacitance change, ESR change, and leakage changes in a biased and an unbiased case, so where the capacitor actually has some voltage on it, or if it's just sitting around idle. And that idle situation might be very applicable to some of these subsystems of a spacecraft, right, where it's not powered. And if it's not powered, the spacecraft is saving power. So that's actually a scenario that's valid out there. And what we're showing is that this capacitor technology is stable in terms of its capacitance to radiation. The cap doesn't really drop, and the dissipation factor or its loss factor doesn't increase, and its leakage doesn't increase. Then not substantially at all, not enough to affect the system performance. So that's a very important thing. Now, a gray is about 100 rads. Basically, a gray is a joule per kilogram, and it comes out to be about 100 rads. Later, we talk about some timing devices and their radiation stability. But as we get microcontrollers and flight actives that are very hardened in the field of radiation, this is very important to look at what the passives can endure without degradation.
So help me understand the x-axis on these plots. I see it going from like M0 to 1500 grays, but then the last one, fifth, is 24 hours, 125C. Help me understand what I'm looking at here.
Yeah, basically, we're looking at the time duration of exposure there. And what we want to see is that this thing is going to be stable over the total dose of exposure. Basically, kind of emulating that of the spacecraft, right? Is it going to be operating at the same efficiency, power ratings, and parameters in the first hour versus X hours down the road? Well, timing, we implied about the much expanded and enhanced digital processing capabilities within these platforms. And that's really very true. And one of the things that's exceptionally important is that of timing. And what we're showing here are some oven-controlled crystal oscillators. There's 3 different series. Let's concentrate on the one on the right. It's actually specifically designed for LEO and MEO. In that, we've got some radiation characteristics. I think it's 60 K-rads for a total ionizing dose capability, and I believe it exceeds that. They have very low sensitivity to acceleration. It's an ultra low phase noise and a high frequency stability timing source. So this is a tremendous type of device. You might use it in a master reference oscillator, or maybe it's LEO or MEO. It's a master clock there, or it might be used in a radar subsystem of LEO or satellite weather radar subcomponent, or even a GPS precision time base. So it's interesting and important to note that there are specific timing devices that have been optimized for LEO or MEO applications as well. And not to downplay the other two series. Basically, those also are very low aging devices. They're low phase noise, they're high stability. Their operating voltages, in some cases, vary a little bit, and the startup power and the power dissipation are a bit different. So depending upon the system, there's 3 immediate applications or opportunities for your application to be chosen here. And actually, there's some other options that are out there with further discussions. But timing is exceptionally important, and stable timing with time and exposure is the real thing to be concerned about.
Yeah, and we've talked about, some of those issues here of aging, radiation tolerance, the extreme temperatures of space. But you mentioned kind of a part of this for the KSP series was resistant to acceleration. It's not just when you're in space, you got to get up there. And that's a lot of acceleration at that launch.
Yes, it's really a really difficult environment. We've got oscillations that are all over the place. We've got stage separation and shock with vibration, multi-axis, and then deceleration. So it's really a complicated situation. And then when you start thinking about, well, we've got a timing device that has to survive that, not show any associated degradation with time or with radiation. Mm-hmm. There's a lot of work, and it's a real art to make something as exacting and high performance as these series.
Yeah, absolutely right.
Well, knowing that we've got all of these blocks within that satellite, we have the potential for cross-band interference or cross-logic interference. Basically, we have to filter potentially as we go from box to box. And what we're showing here are bulkhead filters. We won't spend a lot of time on it. Let's look at the one on the far right. That's more state of the art. Certainly the other 3 are used quite frequently in flight. But let's talk about these miniature parts for miniature satellites. And the part we're looking at the far right, it's a mil-perf part, so it's going to be capable for flight. We could have it in either an L or a C. It could be a straight feed-through as well. It's 3 millimeters in diameter. So that's quite attractive in itself. Its weight might be 0.114 grams. And its cubic volume is 0.018 cc. So really teeny part for isolation of signals between stages. And those advances within the world of ceramic capacitors have helped us to make these ultra miniature bulkhead filters. Knowing that we have uplink and receive functions and transmit functions within the spacecraft, we are offering very low loss options for the PA or low noise, low loss options for the receiver front ends. We're showing a variety of different military grade capacitors on the left. We're showing a COTS type inductor on the right. Interesting to note the frequencies that some of the devices operate at. We can't really say whether your LEO is going to have a L band or a KU or a KA band, right? It could be we just don't know. So we're offering this option, whether you're in the 1 to 2 gigahertz spectrum or the 12 to 18 gigs or 27 to 40, or even lower or higher than that. There's options, and there are flight grade capacitors, even transmission line capacitors that could help optimize that RF block. Let's shift gears a little bit here. We have spoken about passive components where we have electric fields that have, at least in theory, the ability to breach dielectrics and cause failures. Well, in the world of connectors, it's kind of a different world. We have to worry about shock and vibration, of course. We have to worry about other things like outgassing. The ceramic capacitors, of course, are not going to outgas, right? But in the world of connectors, it's a possibility. And then there's also the possibility that exposure in these environments, in the radiation fields, and some of the other reactions that might occur. They could have some parameters that are degradatory in nature to these components, like the connectors. So typically, many times you could say that the connectors are chosen by a class of importance of the mission. If it's a high rail mission, okay, we're flying high rail connectors. And many times, though, these LEOs are going to go with off-the-shelf connectors that maybe seem a bit common, but many times they tend to have a need for simplicity, because simplicity is going to allow us to have less number of things that could be affected, either by shock, vibration, or atomic oxygen, right? So let's look at the most simple type of connector out there. And it's a wire-to-board. Now, that may not be used in all missions. Certainly it won't be. But it's a very simple device. It would allow us to have essentially two sets of tines that come out of the printed circuit board. And the wire would be press fit into that with a very good retention. And it is a shock resistant, and it's a cold weld. So it's not going to be degradation of the connection. There's an optional cap that could go on top of it, a retained cap in some applications, high voltage applications and such. Terrestrial designs were worried about retention more for regulatory agencies on ground. But that probably is not a requirement in flight. And if we take that concept over to the far right, there's a way that we could have coax that would basically connect in a solderless scenario to these cutting tines that pierce the insulation, make that contact to the conductor, and hold it tight. Now, in the world of coax, well, we're limited to less than 6 gigahertz, so this isn't going to be used on KU or KA bands at all, but it's an exceptionally light and miniature solution for small coax runs within subsystems of the RF block. So it's kind of a neat change of thought, right? This is how can we make things exceptionally simplified, and by doing that, less points of failure and actually less weight. Now we could take that in another aspect, and the next slide will show us some of the characteristics of wire-to-board that might be attractive in some designs as well. Now, it's interesting because, granted, we're not at all working on building a space station or anything like that. But back in the space station days, NASA had issued basically a requirement. It was SSP 30426, right? Basically, that put a limit to the molecular decomposition of things and the release of particulates. Now, that's probably not a concern for all LEOs. Well, certainly not a concern for all LEOs. It might be a concern for some LEOs, depending upon their exact functionality. So in some cases, it might be very reasonable and optimal to use the type of press on the right, fairly high amount of currents there, large AWG range, and the like. Certainly not all are going to use that. Now, that's a wire to board. There's really not a lot of wire to wires up in space that are going to use the parts on the far left. However, the downlink stations and the receive stations on Earth, there's probably a high likelihood that they will need that. So this is a neat concept, a fast turn, very physically small, exceptionally light, super simple option for connections. There's some other options that we have when we get into higher density types of devices. We'll next look at a series of parts that have self-locking capabilities. They're very high density with very high pitch counts. So they're tremendous. Now, we'd have to also say, though, much of the LEO hardware probably isn't going to need this type of density. Certainly, ground stations will have an exceptional need for this. And these types of devices would have very high use there. And then the last group of connectors that we talk about, well, that's pretty much the same thing. The next slide talks about board-to-board connectors. These are tremendous devices. They have very good adhesion, very good connectivity, block-to-block or board-to-board. But depending upon the spacecraft and its mission, they may or may not be needed out there. What we could say, though, is that they're high pitched, they're very reasonable current ratings, a very attractive stack height, which is a very important thing as we get into complex board situations. Here again, though, this is much more likely to be used on terrestrial uplinks or downlinks, but there's certainly cases where this could fly.
So, Ron, as I think back to all the things you've covered here, a couple takeaways that I get from this is that the requirements of LEO satellites are quite a bit different from terrestrial applications. And to meet those requirements, you guys have developed a lot of products that are really well suited to those specific applications.
Yes, there's also a lot of data which is available. And that's really critical because we tend to, in the accumulation of that data, we tend to look at extreme use scenarios. We have that radiation database that many customers are not aware of. In fact, many manufacturers do not provide that. It's quite complicated. And then it's really complex and important that you're able to maintain that type of capability with time and designs. So I think the key is, due to the complexity, it's very important to talk upfront and get that correct part selection in there. We could optimize the subsystem, save weight, improve reliability, and possibly even improve cost. Certainly get that design to flight window and time down.
Yeah, that's excellent. It makes a lot of sense that, for people that are getting into these designs to reach out to you guys. You're the experts. You can really help them how to approach these problems. Any other last thoughts before we wrap up for today, Ron?
Well, there's an awful lot of new technology that's coming out. And I think it's important that we continue with the communications. There's a tremendous amount of work being done, both in the military to accelerate their high reliability designs, but also for us to increase the number of parts that are offered in COTS status and the performance of the parts in COTS status. So I guess my prediction will be that you're going to see an acceleration of the performance and capability of our devices. And it's more than just basic parameters like capacitance, inductance, and voltage ratings. It's going to be frequency response, energy rating, radiation capability, and three-dimensional efficiency improvements. So that's my advertisement, and I hope that we can continue to accelerate the rate of our developments here.
Well, that's excellent. As always, it's been great talking to you and learning from you, Ron.
Thanks so much, Dale. Appreciate that. It's great talking with you.
And as we sign off today, we want to thank our sponsor, Mouser Electronics. So if you're looking to purchase any of these great Kyocera AVX products, please head over to Mouser.com to help them continue to support educational presentations like this one. And join us again next time on Tech Chat, where we chat with the leading technical experts like Ron Demcko from industry-leading innovators like Kyocera AVX, who are changing our world every day.